Hello, everyone. Welcome to week 4 of our AI reading group. And today our topic is going to be generative models, AIR, and beyond, the past, present, and future of deep generative vision. So what we're going to be talking about today is I'm going to be talking about generative vision as a field and kind of building it up from the ancient years of 2013 when it really started taking off, all the way to what you're seeing today with, people are claiming all these AI art stuff, Stable Diffusion, all these video generation that, the big companies have been coming out with, Sora from OpenAI. We're going to talk about all of them, or we're going to demystify what they are, what they mean, how they work behind the scenes, and how we got here in the first place. But, and also, if you want to follow along, we have 88 slides today. I do not anticipate to go through all of them, and I'll talk about what we're going to do if we don't go through all of them. But you can come here, this little link here, to follow along on the slides. This is our reading cluster to find on the slides, and after we're done the recording of this talk, we move there as well. I've also written the link here, in case you're halfway through and you want to follow along like that. But first of all, who am I? So I need to do this now because I'm no longer the co-president of ACM AI, but my name is Jordan Lin. I use he, him pronouns. I'm a 4th year CS major, and I have a math minor for no reason. I'm also the former ACM AI co-president. I am now officially retired. You would think I would be less busy when that's the case. Anyway, okay, so in terms of AI stuff, I do research with Professor Bolejo. My lab's actually just down the hall over there. And I do research on generative vision and controllable generation. Don't know what that means? We'll talk about that today. And specifically, most of this presentation is at least tangentially related to my research. So feel free to ask any questions if any of this doesn't make sense, because I do kind of assume you know a bit of the ACM AI capstone track, you're in it at least, and ideally you're also in research track if this is your first time attending any ACM AI events, or if you have done a little bit of machine learning in the past, because I'm not going to go through stuff like what is gradient descent, for example, right? But again, if you have any questions about anything in here, because I try to I do want to make this a presentation for people who have never known anything about generative vision before, just feel free to ask any questions and just raise your hands, and we should be good there. So yeah, okay. So let's start with the table of contents. We're going to be talking about 3 main things today regarding like text image generation and also just generative vision in general. Controllable generation, attack of the LLMs, and let there be time. Specifically, the first section, controllable generation, we're going to be talking about how we can add additional control to these models, so we can give it more information besides a prompt. The second thing, we're going to be talking about how, especially since the middle of 2023, a lot of the modern generative vision papers took a lot of things from large language models. And the third one, we're going to talk about video generation, the current state-of-the-art-ish of that. However, to talk about controllable generation, we need to know what these models even are. We need to know how we even do text image generation in the first place. So I'm going to add a section 0 for that, text image models. But to talk about text-to-image models, we need to talk about how they actually work. So, with diffusion and all that stuff. So that section -1 for diffusion models. But to talk about diffusion models, we need to understand what led us to diffusion models in the first place, the fundamentals of generative vision, like VAEs and GANs. So let's start with section -2. How did we get here? So let's take a trip down memory lane. And before we even start doing that, let's talk about what generative models are in the first place. So who here has done a sort of classification model in the past, like Scipar 10, or is this a picture of a cat or a dog, something like that, or you're in the middle of learning it, right? Okay, a majority of people seem to have done something like that. And these are called what we generally call discriminative model. And what we're doing is we're directly predicting P of Y given X. What the hell is that? That basically means X is our image or our input, if you will, and Y is the label that we're predicting. So specifically, say you have an image of some image, and you want to know the probability that that image is a dog. Then your image will be X, and your Y will be the label dog. So specifically with classification, you're predicting a probability distribution. That is, let's say you have an image. It predicts what's the probability that this image X has the label Y equals bird, has the label Y equals sunset, the label Y equals dog, the label Y equals cat, etc., etc. Right? We're predicting an explicit probability distribution, and we can model that, right? When we do all this math, we have that distribution to work with, and we do a lot of math to that distribution. It's very nice, very direct. However, one thing that has happened in recent years is we have this shift of research to generative modeling, which basically says instead of predicting P of Y given X, we're predicting P of X. And you may be like, what does that mean? What do we mean by P of X? Specifically, what that means is we're learning the distribution of the dataset domain. Particularly, if, we're learning the distribution of the dataset domain. A dataset is basically, we're thinking about the fact that there is some amorphous distribution out there that represents a distribution of all possible images, right? We cannot mathematically represent that, because if we can mathematically represent that, we're done. We don't need to do generative modeling. However, if we keep gathering data sets of images out in the real world, or any data set, like this works for audio, this works for like text generation, what we can do is approximate that distribution. And we want to learn that distribution so we can generate things that are not originally in our data sets, right? So specifically, the data set contains samples from the image distribution, and we want to sample P of X. If you're wondering what that means, I'll talk about it in the next slide. And specifically, we can condition this distribution with stuff. So if P of X just says, what is the probability of, what is this is the distribution of all natural images, then P of X given Y can be something like the distribution of all natural images, given that this image is, say, a dog, right? So you can actually condition the model to give it a more specific distribution. You can narrow things down, and that's what we call conditioning. And if you think about text image generation, this will be your text, your Y, and X will be your image that you're actually generating or sampling. So then here comes the question. Why do we keep using the word sample? Why don't we just do the same thing that we did in classification of predicting the distribution directly? I'll just give you an example of that. Let's think about ImageNet, which is kind of this large scale like classification thing. The images are 256 by 256 pixels by 3 because RGB, and there are 1,000 classes. Right? Do you have a question? Okay. So in classification, P of Y given X is one entry, because this Y is just one label, right? It's a probability of is a dog, or is a cat, or is it whatever class that we have. So it is one entry, it's one dimensional, it's one thing, it's a scalar. And it has 1,000 possible values, because it can either be, if we have 1,000 classes, we can index it from 0 to 999, right? So it only has 1,000 possible values. So our output is 1 by 1,000. So we have 1,000 sort of probability values, and that makes up a probability distribution. That's pretty manageable as an output from the neural network. Then we think about generation in the context of the images. We have this many pixels. Each pixel has 256 possible values, and that's just assuming 8-bit images. If you have images that are, say, 10-bit, or even if you use a continuous representation, this can be infinite number of values. Then your output, if you want to predict this probability directly, is 256 by 256 by 3 by 256. That is impractical to predict directly. We shouldn't have to predict, yes, this represents very nicely the probability that a given pixel on this image is going to be, say, all of the value, say, 127 middle array. But that's very impractical, and there must be better ways for us to predict this stuff. Therefore, we train models instead to sample P of X given Y, aka every time we call the model, it randomly gives us a new value of what that one pixel would be. So in this case, I'll give an analogy in terms of classification. When we directly predict the distribution, I'll say this is, by the way, a fraud from Cyberton. Cyberton is actually not as easy to think. Sometimes you look at it as a human, you're like, what the hell is this thing, right? You ask the model what it is, and it gives you a distribution, right? Let's say 0.8 here is fraud. So it gives you a distribution. When you are sampling from the distribution, it has a 0.8 chance of giving you fraud, a 0.1 chance of, say, giving you dog, 0.05 chance of giving you cat, et cetera, et cetera. So you can see how now suddenly the output is a lot less in the number of dimensions, but suddenly we're not predicting the probabilities directly. And that makes things also more challenging. And that's basically what we're doing with generative modeling. So we're sampling the model, and we're saying, okay, every time I sample this model, I want to pick for our data distribution. Hopefully, if our model is well trained, we'll pick something that is high probability, right? And in this case, high probability means it generates an image that looks natural. It looks like an image. It looks like something that would belong in our data set, but hopefully is not in our data set because our model has some memorized things. So that's the idea of generative modeling nowadays, and what our goals are. Does it kind of make sense so far? Okay. So I'm going to start with talking about autoregressive models, which is one of the few models which does actually directly predict the probability of of like the image itself. So like instead of doing sampling, it actually predicts the probability distribution. And I'm going to talk about one of the earlier examples, which is pixel RNN and pixel CNN. To this day, I don't know what the exact difference between these two is. They're very similar. They're from the exact same, like almost list of authors. But the idea is that what if we predicted the distribution directly anyway? And we start, say, with an image. We start with the first pixel, and we can predict the second pixel or any subsequent pixels by looking at pixels to the top left-hand corner of it. So we have this kind of like dependency over there. So then the way when you're generating will be you predict the first pixel, you predict the second pixel, you predict the third pixel, the fourth, the fifth, the sixth, and so on and so forth. Because you're predicting one pixel at a time, we call this autoregressive. You know, you may have seen this in large language models of like next token prediction. This is very similar to that. Because the output space is only, say, 256 by 3, because you have 256 values and 3 RGB values, this is a lot more manageable, right? So, like, literally, like, we're literally just doing 256 classification, and the only two differences between these two papers is one uses an RNN, specifically LSTM model, and one uses a CNN backbone, right? And you can just drag along the image and generate images like that. However, the problem with this is it's not very scalable. Like, I severely overestimated the resolution of this predictor. But like one of the things is that they tested on the image data set, which is 1,000 classes. You can see like examples of these classes here. A lot of the images don't look too great. It's because the problem with autoregressive models, at least with what we have so far, is as you are all the way down here, because of the constraints of either CNNs or RNNs, it's hard for you to attend to everything that's before it, right? When you're here, near the end of the image, to get information for everything before it, it becomes very challenging, right? And especially if you want to scale up to much bigger images, this becomes a lot more challenging. So we don't really do this anymore. Again, yeah, it's not scalable, sort of.
Could you just, like with a,
yeah,
when people try this to transform, like on the pixels?
Well, sort of. Ever since we scaled our transformer, people have been trying to make these models work again. Yeah. But we're not going to talk about that today because of time.
Okay.
Yes, okay. So then we move to a second idea in generative modeling, which this is going to be now key. We're still using this today, at least as part of what we're doing when we're generating. And to do this, I'm going to first introduce the idea of an autoencoder. So the autoencoder, it's really a model that is for the task, or a paradigm that is for the task of compressing information. Specifically, when you have an image, it's very high dimensional, you know, like 256 by 256 by 3. That's a lot of dimensions. Like you can imagine that as a vector in a super high dimensional space. However, not all those dimensions are useful. We can often compress that information into much lower dimensions, like say just a 128 dimensional vector. And that's exactly what autoencoders do. You have an encoder and you have a decoder. And all it does is you give it an image and encodes it to some much lower dimensional vector. We call this a latent. And then we just decode that latent by using, you know, this can be a convolution neural network, and this can be like an inverse convolution neural network, this convolution neural network with transpose convolutions, aka convolutions that make things bigger. And you just try to reconstruct the original image. Because the model, if the model is trained well, because it has to reconstruct the original image, and it's reconstructing this image purely from this much lower dimensional representation, then this much lower dimensional representation must necessarily contain sufficient information that encodes enough information for the whole image, because it has to be able to reconstruct it, right? So that's what an autoencoder is. And people have used this a lot for, say, like image denoising. You can start with a noisy image and a denoised image, or image reconstruction, because they would start with an image that has some parts masked off, and you want to try to predict what that masking is, or we call that in painting as well. But you know, you can do this for a lot of tasks, and people have been doing it for a very long time for a lot of things. Like the very first asterisk, like VAE was proposed in 1987, for example, and this is like way before like the deep learning revolution of 2012. So yeah, like again, it's very. However, this gives us something that's very nice, because it is very difficult to directly model the image distribution itself. As you can see, it's very high dimensional, but it is much easier to model this much smaller latent distribution. So how can we take advantage of this? Here comes the variational autoencoder. So the variational autoencoder is basically an autoencoder that allows you to stochastically, aka randomly, sample the latent that's inside, sort of. The idea is that you have, like we tell you know what an autoencoder is, which is, you know, we can't sample the distribution, but you can sample a latent space, and we actually want to make the latent space actually sampleable, because we don't want to just like for us to generate an image every time, to have that latent space be encoded by an existing image. Like why would you want to, like that defeats the purpose of generation. So instead, what a VAE does is instead of predicting that latent Z directly, it predicts a mean and standard deviation. And it uses that mean and standard deviation then to randomly sample, to basically multiply and scale some randomly generated Gaussian distribution, and then it reconstructs it. So it's almost a regularization thing that allows the space inside to be much smoother, because given a mean and standard deviation, you have to reconstruct an image. So then the latent representation, instead of just being some vector for any given image, which may not be smooth, because if you just encode a bunch of images, there's no guarantee that that internal latent space is very nice and smooth. But by doing this, you're forcing the internal representation to be a Gaussian distribution. And there's some math that guarantees that this can sort of happen. I'm not gonna go for that today, but the idea is that then you can maybe sample things from the middle, or at least have a very nice interpretable latent space. And again, like to kind of like, if you want to know what each of these terms mean, this basically means given the latency, the decoder has to reconstruct the original data. So this is kind of like our reconstruction loss. And this over here says the latency must match the Gaussian distribution. So it has this constraint of like, okay, our internal latent distribution must be nice and smooth. And this does kind of actually work. If you want to generate such modified images with VAEs, when we have a given image, what we can do is we can start traversing this latent space, and we can actually interpolate between different images. Like for example, here, this is one of the earliest examples. If you have 4 expressions of a person, you can just kind of project them or like encode them into this latent space and start interpolating inside this latent space. And you can actually have this effect where you're like interpolating between images. So we're starting to generate some new images by interpolating between them. And this kind of also shows that whatever's inside this latent space, this compressed low-dimensional space, by doing this sort of Gaussian regularization, is smooth. And we can do a lot of fun stuff with it. And it's also very useful for just normal computer vision tasks, where we need a good representation of an image. For those of you who are interested, I recommend reading this blog from Autoencoder Beta VAE, from like, I believe one of the research scientists at OpenAI. He has written really, really good blog posts on kind of like the history of VAEs and goes through some of the math as well. Then we get to something that actually starts generating pretty decent looking images, which is the VQVAE, or vector quantized VAE. For those of you here who have done LLMs before, this may look a little bit familiar. And that's because instead of having a continuous smooth Gaussian latent space, the one change they make to this VAE is that they say, we maintain instead a set of tokens / embeddings / codes, as our team really likes that, in the latent space, and then we quantize our encoder output, Z, to the codebook. Specifically, what we do is every time when we encode an image, right, when you're training the image, you encode it with an encoder and you get some sort of latency, right? Then what happens, you basically say, okay, given this latency, I would define in my codebook that's also randomly initialized the token that is closest to it in, like, say, Euclidean distance. And it basically just says, all right, I'm going to take that token and I'm going to use that instead. So you may be like, okay, because you have a discrete number of tokens, that seems like this is much less representative than a continuous distribution, right? But what it turns out, as we also have learned in lessons from large language models and just transformers and language modeling in general, is that this actually often improves image quality, because instead of just encoding into one token, we typically encode into some number of tokens, some combination of tokens in specific order. So in a specific case of the original VQVAE, they chose 512 tokens out of a dictionary of not 512 tokens. They chose 32 by 32 tokens out of a library of, say, 512 tokens. And you can imagine how, like, in 32 by 32 tokens, the order of those tokens and the actual tokens you select to be put into it, because you can have repeated tokens, creates a lot of different combinations of pictures, way more than that is practical. So we have still that almost continuous quality to it. But because it's discretized, intuitively, what the model can do is learn specific features for each of these tokens, and you can actually learn things usually much better and create specifically much sharper images. Like, one of the things with VAEs is that the images outputs are usually very smooth and very average looking, and the reason is because that's exactly what it's doing. If it always just kind of predicts the average, it will get the least loss, at least for the time being, right? It's a sort of local minimum that it gets stuck at. However, with vector quantized models, you're forcing it to have to learn discrete concepts. And this works very well. Like, specifically the loss, it does two things. It says, first, the embeddings must be close to the encoder, Z. So basically it says, whatever we encode, the embedding which is closest to it must be, we're driving that embedding to be closer to whatever we encoded. And then we also say the same thing, which is whatever embedding that we have chose, the embedded result, that latency, also has to be close to it. But we put a stop gradient on each of the ones. So this one specifically changes the embedding, and this one specifically changes the actual like encoder itself. So by doing this kind of two-step process, you're kind of making sure that they don't pass gradients into each other, so they don't almost do like an adversarial attack on each other. SG means stop gradients, so you're actually not passing gradients through these. So by doing so, you can actually very effectively learn a really great encoder. Yes?
Is there a method of getting a very good embedding space for the variational autoencoder?
Oh, for variational.
I mean for the BQ VAEs.
Yeah, so basically, we don't really have that sort of nice embedding space representation anymore because we just have a bunch of discrete tokens, right? And that's our embedding space. So we no longer have that guarantee. So interpolating between things gets more difficult. However, we actually get much higher quality images. And then at this point, people want to generate images, right? Yes.
Wait, so, okay, you have the vector in the middle.
Yes.
And instead now, you just have like a list of bases that you can like project that vector, or like you try to approximate that vector with like the bases that reconstructed hold it the best?
It's not even that. It's just when you encode this image, so you start with a 256 by 256 image.
Yeah.
You use a CNN to compress down to say 32 by 32 by 1.
Yeah, you're latent.
Yeah. Each of those 32 by 32 sort of feature has, say, a dimension of, say, 1024, right? So you have 32 by 32 tokens. And you're saying, for those 32 by 32 tokens, for each of them, find the embedding inside our codebook that's the closest to it.
You only pick one.
You only pick one. You pick the top one. Yeah.
Okay.
So it's a lot more LM-like. Like you're almost doing like a pseudo classification task, like, but you're just using your assistance.
It feels like you're like, not like quantizing, but you're like.
You're quantizing. You're quantizing your feature space to your embedding space. And you're joining learning them.
Yeah. You don't have enough, then you can't.
Yeah.
That's surprising.
Yeah, you can use closest embedding.
Surprising.
Yeah.
Cool.
It's pretty cool. And like, okay, one of the things is that then what we can do is, because we have a list of tokens, we know how to deal with generating a list of tokens. So they just took a pixel CNN, if you remember what that is, right? Before, the problem with pixel CNN, if you remember, is that because we're auto-regressively predicting the next token, it's very difficult for us to scale up, right? However, because we are compressing down to a much lower dimensional latent space, we can actually train a pretty effective pixel CNN to predict these tokens instead.
Wait, predict like one vector or multiple?
Multiple. You start with the first vector, maybe you randomly pick it or whatever, right? You start with the first vector and you ask your pixel CNN to say, what's my second vector? What's my third embedding? What's my fourth embedding? And you fill up a 32 by 32 embedding and you decode it. So you first train a VAE, and then you train a pixel CNN to predict the tokens inside to generate images.
Wait. The embedding, okay, wait. The embedding, what's the dimension? I'm confused. You have this latent vector.
Yeah.
How big is that latent vector? Like,
so let's say 1024, right?
1024.
And you have to say 512 of those 1024 vectors.
Okay, and you just find the closest one.
Yes.
Yeah. So what is the CNN predicting here?
We start with the first vector, say
entire 1,000 vector.
Yeah. It predicts, because there's only 512 of them. It says out of the 512, say index 26. Yeah. Then based on my previous index is 26, now I want 41. Now I want 128. Now I want this. So it just predicts a list of tokens, like how LLMs do their things. Yeah.
What is that useful for?
The thing is, if you can predict a list of tokens and you just decode it, you have an image.
I thought you're using a single token to do the image.
No, you're doing 32 by 32 tokens, at least in the case of BQVH.
Oh,
yeah.
Okay.
So it's like,
when you predict it, it's 1,024. You said
exactly. So to reiterate, we're encoding an image into a list of tokens.
Okay.
And then we're using a pixel CNN to predict that list of tokens when we're generating things after we have already trained the BQVAE.
And in the approximation, each token, you try to find the one in the book that's closest. And then, you have 32 of them. Okay.
Yeah.
And then you can sequentially.
And the nice thing is, because then we're just doing direct prediction, right? We're doing direct, like explicit multi-class prediction of like, out of these 512 tokens, which one do I pick?
Why couldn't you just have a single vector and then the larger cookbook and then just predict?
The thing is, if you have a single vector and say your code book's 1024, you only have 1024 possible images. However, if you have a combination of images because of combinatorics, it suddenly explodes out into a huge number of images you can generate, right?
That's cool.
So that's the idea. So keep this VQVE in mind. Just kind of put it to the side. Yes.
So the first term would only backpropagate through the decoder, right? And
yes.
The second term would only
through
the
the second term will only backpropagate to the embedding Okay. And the third term only only propagates to the encoder. Okay. So it's kind of like you're learning the three things, separately, sort of. So yeah, keep this VQV at the back of your mind because it comes back later. But we're going to get to another paradigm right before diffusion models that's still kind of used today, which is something called generative adversarial networks. Okay, so this is something that is quite different and probably the most odd one out of everything that we're going to be looking at today. Specifically, it was first proposed by Goodfellow et al. In 2015. Well, it's still one of the best deep learning book authors, amazing stuff. But specifically, here we have two models instead of just one model. We have a generator and we have the discriminator. And their respective goals are this. The generator takes some noise, like say 128-dimensional noise, and it generates a fake image. Then the discriminator takes that fake image, or just takes any image, and tries to do a binary classification of, is this image real, aka from the data sets, or is this image fake, aka generated by the generator? The generator is trained to fool the discriminator. It wants to make the discriminator as bad as possible. Specifically, it wants its fake images to be identified as real. The discriminator wants to obviously identify real images and fake images correctly. So they have this adversarial loss, this sort of loss that there are fundamentally at odds with each other. And we just train them. We train them together. We jointly train them. And the nice thing is, theoretically, this should work because this is what we call like a sort of two-player game that we can that was proposed by Nash, and we should, in the ideal case, reach what we call a Nash equilibrium, which is basically because the generator is perfect, aka matches the data distribution directly, and the images it predicts is indistinguishable from images from the data set, and the discriminator thus has to randomly guess. And the reason is this: when we start out, the black dotted line here is our, say, actual data distribution. The green line here is our generator, and the blue line here is our discriminator, right? So when we start out, the generator is very far away from the data distribution. It's just generating random noise. And the discriminators are just taking random guesses. So it looks very janky like this. However, as we train the model, as we train both of them, the generator should get closer and closer to the data distribution while the discriminator gets better and better and better. However, at a certain point, when a generator gets so perfect to the distribution, the discriminator cannot tell the difference. So it just has to guess rapidly. That's the idea. That's the ideal case. You can hopefully see how this is very unstable to train. Like one of the, a very early, especially GAN research is that how do we make it actually trainable and how do we make it easier to train? Because there's a lot of problems that come with GAN training, such as mode collapse. For example, the generator has found a specific type of image the discriminator happens to be really bad at predicting. It just keeps generating those images, even though those images don't look good, looks artifacty. But because the discriminator happens to be really bad at it, the generator just keeps generating that. So you can run into a lot of problems with training generative adversarial networks. And so this is basically a generative adversarial network, but then the very first paper just used a normal fully connected neural network. But the second one, they just said, hey, what if we just use convolutions? Guys, convolutions, vision, right? So they used convolutions and it actually started working very well, right? So you can generate a little bit better looking images, and you can actually do this yourself as well. Especially if you follow the original hyperparameters from the paper, you can pretty much recreate this paper decently easily nowadays. However, one key observation they make with generative adversarial networks is that we start with this random noise vector, right? And we generate and reconstruct the image with a bunch of inverse convolutions. What they noticed is that over time, this space becomes interpretable. What that means is if we just start with a random noise vector, assuming a well-trained GAN model, and we start with another noise vector, what we can do is interpolate between them. And we get this really smooth, nice interpolation between two images. So the authors concluded that this, when you're training this on a data set, actually becomes a really good representation of your data set, kind of like a VAE. That VAE, we also call this a latent. Because again, it's like a much lower dimensional representation of the model. But then this is very interesting because we never got this by explicitly trying to compress the image. We only got this because the only thing that the whole model relies on to generate an image is this noise. So this noise, this space here, better be very interpretable because it has to necessarily encode the information you need to generate the image in the end. So when you're training it, it becomes very interpretable space. So that's what DCGAN or Deep Generative Adversarial Networks did. Then I want to take a slight detour to talk about a paper that was happening around the same time-ish, which is people were trying to do this task of style transfer. Relatively explanatory. You have some sort of style image, you have some sort of content image. You're trying to transfer the style of this style image to a content image like that, right? So this is a task that people have been working on for a while. And this paper, arbitrary style transfer in real time with ADA-in or adaptive instant normalization, introduces something called ADA-in. That basically what it does is it renormalizes it given some sort of intermediate feature. So like let's say you're inside of a general model, inside some model. You first normalize that intermediate feature, then you scale it by some new bias and scale. And this bias and scale is learned through some sort of, it's usually learned through a fully connected neural network. So what you would do is you're predicting the bias and scale that actually does the scaling directly. And what they found is when they use this inside of a Vichy encoder and they train a decoder alongside with it, they can actually, so this is kind of basically NBA, but like slightly bigger. What they can do is they realize they can actually simply by taking this image, take their intermediate features, take this image's intermediate feature, or like encode this image and predict scale and biases to scale this image. And by doing so, you're able to do stylization. In other words, our takeaway from this is the content, especially appearance of an image, can be determined or at least influenced by the intermediate statistics of our distribution. And all we have to do is change that distribution, change that statistic to generate images with different appearances, to transfer styles, etc. So with that in mind, here comes style GAN, which takes this idea and applies it to generative adversarial networks to generate really, really high quality looking images, especially for 2017, right? Like, I know like to you guys, like nowadays this is not anything impressive. You're like just faces of people. This was really good back then. So this is 2017. And specifically, this is an architecture paper that says, instead of doing what we did with DCGAN, which is we start with some latent noise and just kind of blow it all the way back up to an image, we instead separated it into two separate networks, a mapping network and a synthesis network. Specifically, what a mapping network does is it takes our same latent, randomly generated noise. It passes it through like a bunch of fully connected layers with radius in between. And that gets us a W vector. This is also a latent vector, but it's a slightly better latent vector because we've managed to encode it in some way. And specifically, then we have a synthesis network that starts with some constant value. This noise is solo learnable. And then this W model then goes through a bunch of linear layers to then normalize this value as it gets kind of blown up. Why is this very important? And by the way, this is also the, I don't know if you guys see this. This person does not exist.com, which is a website that every time you refresh, gives you an image of a person that does not exist. So, and here's the thing. The backbone of this website is the style GAN. I remember this being a pretty big-ish thing when it first came out back in the day. People were like, whoa, that's crazy. AI is going to take over the world. We're so young and so naive. But yeah, like this, the backbone of this is the style GAN. And it kind of goes to show how incredibly powerful these things are. And specifically, because unlike DCGAN over here, where the connection between, say, like this Z and say some higher layer here, it has to go through a lot to get there, which means there's sort of less sort of coupling between real semantic features between our final generated image and the Z. Because our W embedding space here is directly influencing the statistics of even the highest layers, this W vector has to be even more interpretable, even smoother, and even more disentangled than our latency at the start. And that's what we see. Is what we can do is at different resolution levels, we can actually combine the W vectors of different images to create really, really good sort of like mixing of appearances. And you can also interpolate things really well. So our W space is what we call much more disentangled. And to give you an example, think of, say, let's say, we have a data set where there are two types of people in that data set. Someone who's sad and without glasses, and someone who's happy and wearing glasses, right? If we were to train a GAN on a normal GAN on that model, and we were to interpolate, say, and we somehow find a direction that says, oh, this direction makes people have glasses, the direction of person with glasses and the direction of person smiling will be the same. Well, it will be very, very close to each other, right? Because that just happens to be how our data set is. However, what style GAN addresses is that by doing this sort of learning where our latent is more directly affecting the outputs, what we're able to do is disentangle this. Because so the directions that we find for direction for person wearing glasses and direction for person smiling all the times is more disentangled. There are two different directions, orthogonal, if you will. And that's what StyleGAN is able to do.
How does that? I don't get the intuition. So like, how does it implicitly? Like, is it the architecture? Because it is the architecture. Normalized. It's like you're scaling the distribution of like with the like if you go back to the like
basically what it's doing is it's taking this like completely randomly distributed latency, which is a Gaussian distribution that has really nothing special about it. And the only thing special about it is, in the original VC GAN, it can interpret it to mean, like, oh, it's a smooth space, right? Like every single thing in this Gaussian distribution means something, can traverse in between it. Because we have this mapping network, what this mapping network does is basically takes this Gaussian distribution and puts it into a much more complex distribution that it has the ability to encode these much more semantic directions. So a visualization is like, start with this sort of like this is the distribution of features in training sets. Say like, like this person wearing glasses, what's the color of their hair, complexion of their skin, how big are their eyes, are they wearing glasses, are they smiling? What we can do is the mapping network can map the Z feature to something that way more resembles this amorphous distribution of training of features, if that makes any sense. And it has to be able to do that because this W space is directly affecting the actual outputs of the image.
What happens if you just grab that random vector and then fed it into the ADN?
Oh, just
from there, right, to all those.
I actually don't know. I've never tried this, but I would imagine it not working very well because what you're then doing is you're basically taking random noise and you're using this random noise to scale the last layer of a generative adversarial network, And you're using random noise to scale things is never really a good idea. Like even though you're only doing one projection, right? So if you're only doing one projection, that's usually still going to be random noise. It's probably not going to be very good. We need way more layers of kind of like modifying that latence to be able to make sure the feature that we're doing this normalization to actually means something and is not just resembling random noise.
Before we had it, so the convolutions were the one doing the information, right?
Yes. But now the convolutions are really just upsamplers. They're making images look like images, but they're not really the deciders of this image should look like this. That's decided by these added-in layers. Okay.
So it's mainly that, like, would you say it's the add-in that can give it that more disentangled?
Added-in is merely a way for us to say, we have some feature, let's give it that. Added-in is a part of, because instead of the noise being affecting the image from the very beginning, like DC GANs, this latent is not affecting every single layer all the way until the very, very last layer. So necessarily, it has to be more disentangled, contain more features. It can't just be random noise anymore.
Yeah.
So that's the idea. Okay, so the summary of what we have talked about before. The pattern is like a lot of these seem very unstable and kind of jank. Like VAEs and autoregressive models hit a scaling bottleneck very early on, and GANs, however, and still are kind of amazing. Like we still use like the adversarial training all the time. But another thing is these models are very data set dependent. You may have seen like most of these have so far been tested on data sets such as Cypark10 or like ImageNet is still kind of a small model, so only 1 million images, and like Celeb A, which is just like a faces of a bunch of celebrities. It was the wild west of the internet. People could do that back then. But the data sets were very constrained to a smaller domain, except for Big GAN, which attempted to scale up to ImageNet, but it was still just ImageNet. Like it was never like all possible images scraped from the internet, right? We couldn't do that back then. So then the question becomes, also we were still limited to at most class image pairs. We're conditioning on the class, like it's dog, it's a cat, etc. Question becomes, how do we go big?
Wait, why were we conditioning on classes still?
If we do ImageNet, we want to condition on classes because ImageNet gives us class information of like this image is a dog, this image is a cat, this is an image of a flower, etc.
I mean, we didn't have to though. Like
we didn't have to, but it makes the results look a lot better.
Because you could separate like dog.
And like for style, there are also options to condition on a class. Like people have been doing conditioning for a long time. Yeah. Then get to part -1. Diffusion models. I don't know. Okay. All right. Okay. Part -1 diffusion models. We may not get to the last section today, but we'll try our best. So I want to first start with a sort of an intuition of how these models work, and this is the backbone of a lot of modern text-to-image models nowadays. So here, imagine this space where we have a sort of probability distribution of like this is technically just a 2x2 space. We can imagine with images how this is pretty much higher dimension. A darker color means a higher data probability. Specifically, what PX means is given an image X, what is the probability that it is within our data distribution? So an image, like say this, a normal looking image, like an image of my cat, who's clearly very happy to see me. He hates my camera so much because of the shutter sound. But what this really means is that if an image is normal looking, and you were to say this then in this implicit distribution, its probability will be pretty high, right? However, if you keep going out into a space where it's, say, very noisy, then the probability will become lower and lower and lower. So that's the idea, right? So that means if we can model P of X well, then we can sample from P of X. Because of how probability distribution works, we will only really get back results that are high in probability. It's very rare that we're going to sample low probability data. We're only going to get a high probability data. So this is how we model general models, which is if we can train a P of X well, or we can train a model of P of X very well, then when we sample it, we get back really high quality images.
Yes. Explain how do we sample a model? How does it learn? Is that?
Well, sampling a model is just to ask to generate an output. So, and like this P of X, like it's very like, again, like this is just a mathematical way that we're using to represent things. It's not really practical in the sense that this is how we go about understanding it, and we can model math ways to like actually make our.
What is the actual like network here? Like what is that thing, and what is the ML sample? Like I'm gonna sample from the.
And we're gonna talk about that.
Oh, that's gonna be great.
Okay, so we don't generate natural images. So then the task becomes, if we know it's very easy for us to generate random noise, right? We can generate Gaussian distributions very easily. How do we travel from this point to this point? And that's basically what diffusion models do. We start from some noise and we travel all the way to high data probability. In other words, we're denoising the image. So that's how one of the first formulations of diffusion models came to be, the DDPM, or the denoising diffusion probabilistic models. It is basically a denoiser that is so good, it generates an image from pure noise. That's the basic idea. And specifically, what it does is it first defines something called a forward process. You have an image, you iteratively add noise to it. And then it defines a backward process that we learn. Specifically, given some noisy image, some xt step, we want to predict how we can get to x of t minus 1. How we can denoise the image just by a little bit. And then we pass it back in the model. Denoise it a little bit more. We pass it back in the model. We denoise it a little bit more, etc., etc., etc. And this model is conditioned on t, so it actually knows the noise level of the image. Because again, when we're generating an image, we know the noise level. So, and then in this case of the DDPM, it had 1,000 time steps, 1,000 different noise levels. 0 is no noise. Big T is maximum noise, or 1,000 is maximum noise. However, specifically, instead of learning, given x of t, what x of t minus 1 is, we instead learn the noise that was added in the step. Specifically, let's take a look at our actual training. So what we do is we first draw a random piece of data from the data distribution, aka we take an image from the data sets. Then we sample some random time step t, right? And then we also sample some random Gaussian noise. So we can generate some random Gaussian noise. Then this is what we do. First, we add noise to the image based on our noise schedule. This alpha and 1 minus alpha situation is basically just making sure that as t equals 0, it is just this x0, and when it's at t equals 1, or at t equals maximum, then we have just the noise here, right? So we first add noise to the image. Then we pass that resulting noise to the image, and we pass it into our model. Epsilon theta here means the model, epsilon just our noise. So when you see a subscript theta with some symbol, that usually means in machine learning literature that it is a trainable model, because theta is our parameters. This model, given the amount of noise t, predicts the noise that was added, aka it predicts what we added here. Then we minimize the error between our predicted noise, which is this thing, and the actual noise that we have added. Does that make sense so far? So what we're doing is we're predicting at each step what noise do we add, basically. And specifically, it is predicting how do we get from this noisy image, that noise, how do we get the noise that got us from the clean image all the way to the noisy image? Yes?
How do you quantify noise mathematically? What does it look like?
Oh, noise?
I know what it is.
Yeah. It's this, right? And then to quantify mathematically, it's a sample drawn from the Gaussian distribution, basically.
for like each pixel.
For each pixel, yeah. That's essentially what it is. Yeah, out of like each of these, we do a random generation of this pixel, like all of the RGB values, right? So that's how we train things. And to then generate images, to do inference, we start with some Gaussian noise x of t, right? We start with maximally noised image. Then here's what we do. First, we predict these two are the same, so we'll just do this separately. We first predict the noise in xt. So for any given time step, we predict what was the noise that was added to me to get me to this point. Then we subtract the predicted noise from the actual image itself, from the inputs, to get a predicted denoised image. So it basically says we are at x of we're coming at x of t. I want to know the noise, predicted noise that got from x of 0 all the way to x of t, and then we're subtracting that noise away to get to x of 0. And then we add slightly less predicted noise back, and it's that same amount of predicted noise, so we get to the predicted x of t minus 1. And then, okay, and basically we do this iteratively all the way from x of t to x of 0, and that's how we generate an image. And here's the nice thing. We can skip time steps as well to accelerate the inference. Specifically, instead of going from x of t to x of t minus 1, we can do like from x of t to say x of t minus 50. So instead of having to do 1,000 model calls, we can just do say like 50 model calls, for example, and dramatically speed up inference. Yes?
Wait, why are we adding prediction noise back into it to try and get back to like the unnoise of it?
Right. So the reason is because when we start with a completely noised image and we were to ask for predicted noise to get us all the way to x0, our clean image, it's probably a really, really bad prediction, right? Because we're basically asking it to just go from noise all the way to image. So because it's a really, really bad looking image, what we basically say is, okay, you're going all the way here, but then we want to add it back to a little bit before so we can almost do this prediction again. So it's almost calling itself continuously. So it makes any mistake in that x0 prediction, it has a chance to correct itself because it has this iterative process. Does that kind of make sense? Kind of, right? The reason why this may not make sense, like like theoretically speaking, is because I'm simplifying a little bit here. The original DDPM paper actually has a specific reason for doing this. Like if you actually look at the paper itself, there's a lot of math, right? There's a lot of math. Like specifically, it really tries to motivate exactly why we do stuff like this, and it basically realized that before the process of adding noise at every single time step can be parameterized as just adding noise from x0 all the way to xt in one go. And then if you do a bit of like probability shuffling around, you can figure out like, oh, this is the mathematical equivalent way to actually sample things. And specifically, this idea of skipping time steps actually came from a later paper called DDIM, the Denoising Diffusion Implicit Models. That basically says the original DDPM is basically equivalent to doing this sort of predicted x0, putting it back to xt, and then adding some bit of random noise. And this bit of random noise, or we call stochasticity, basically adds a bit of extra random noise every time we do this pointing back to x of t. And what that does is basically perturbs this generation process a little bit. So the model makes a really big unrecoverable error in predicting what that noise is. Injecting this additional noise basically tells us saying, okay, I'm pushing you around randomly a little bit, get out of this really weird, bad situation that you're getting yourself into. So generally, these sort of random noise will improve generation quality a little bit. So yeah, like that's basically what I was saying. The original paper had this random noise as one fixed value, but then DIM basically says, hey, this iterative noise adding doesn't really matter. We can just do this kind of like x0 prediction thing. So like this is actually more accurately what we're doing is every time we're going all the way to x0 and then going back to x2. And we're going all the way to x0 and going back to x1. And this going back and forth is the predicted noise of the model. That change, that delta, is exactly what we're predicting. Yes.
No, just because like adding a bunch of Gaussian noise is one big Gaussian noise, or is it more complicated?
It's basically that. It's like adding a bunch of Gaussian noise, even when randomly, can be modeled as just adding one big Gaussian noise.
Okay.
Yeah. Okay. So this is when Yang Song came in. So around the same time, he was also coming up with a formulation of diffusion models, but from a different perspective. Instead of this kind of Markov chain noise adding back and forth, he basically just said, well, it's just a stochastic differential equation, right? Specifically, we have two distributions. We have our data distribution and we have our noise distribution. What we're doing is we're essentially saying, as we add noise to the image, we're changing this distribution, shifting into this noise distribution. Then by learning this kind of delta, like at each of these points, how do we get from here to here? By learning this delta, what we can say is when we start from a noise distribution, we just use the same delta, but subtracting it to get to our data distribution. So the denoising process is really just an ordinary differential equation path, and we can do a lot of stuff with that. But then, like, there's a lot of math behind it. But then the idea is that you can traverse your way literally from the noise distribution to the data distribution. And the way he initially proposed this is like, oh, it's just the stochastic differential equation he used as a result from this 1982 paper, which this guy was like, oh, the diffusion process, they weren't using for images at the time, they were using for some physics stuff. And they were like, oh, we can actually solve this differential equation. And Janssen looked this up, wait, we can use that for images, and he used it. And then Karas et al., fun fact, same first author as Stalman, came in and said, okay, all this stuff, like all this probability Markov chain stuff, and then this stuff, they're actually just the same thing. It's actually all just specific cases of my generalized ordinary differential equation formulation. That's kind of what we use nowadays. Is everything is just an ordinary differential equation when we're dealing with diffusion models. This is our current understanding of this. Sort of. The takeaway that you should take away is we showed a model how to map from data to noise, and the model learns to map from noise to data iteratively. So that's the takeaway I think you should have from all of this. And specifically, to recap, the for process shows us how to go from high data density all the way to low data density by adding noise. And by learning this process, by learning this delta of how we're changing things, we can reverse it with the backward process when we're denoising the actual image, where the model learns to start from some low data density region and to traverse itself to a high data density region. Does that make sense? Okay, so that's what diffusion models are. And here are some good resources from actually learning about it. This blog was absolutely insane. It gives you like 13 different reference ways of looking at what a diffusion model is, because there is that many ways of looking at it. And this is the original presentation by Janssen that basically motivates a lot of the details of why he designed these generative models in that way. And just another quick thing, you may be wondering, okay, what is the actual model that is behind this process? What's the actual neural network that you're learning? And at this point, it's generally units. Specifically, what a unit is kind of similar to an autoencoder, but because we're not necessarily trying to compress an image, you're basically starting with a bunch of convolutions, you're downsampling, and you're reconstructing it. But because we're not necessarily trying to learn the representation, we're just trying to have a sort of bottlenecked situation where we're extracting the most important information and deconstructing that. We have these long skip connections, which kind of comes from ResNets, to basically make the model work a little bit better. And specifically, the original unit was used for image segmentation, specifically medical segmentation. It beat out all the competition at that time by so much that everyone immediately switched to it. It was crazy back in 2015. But the idea is that our inputs and outputs are the same dimension. And that's good because what we're doing with diffusion models is our input is an image, noise image usually, and our output is a noise of the same dimension. So this is a very good architecture for us to use. And around this time, people would condition these models on the time step, and they use something called sinusoidal embedding. At some point in the future, our team will do an LM talk, and he'll definitely talk about what this is. And also, we use self-attention layers. Raise your hand if you've heard of transformers before. Okay, good. I don't have to go through it. That's very nice. But basically, you have a bunch of self-attention layers inside that basically kind of enforces self-coherence as well. Okay, so that's the model behind it. Then we finally get to part 0, which are text-to-image models, and which is, hey, look, I can generate anything now. And I'm going to be talking about a few things in this. First, we're going to talk about class conditioning in a little bit more detail and how we actually condition things in the first place. Then we're going to talk about text conditioning. We're going to talk about the sort of what OpenAI and Google's early efforts into this, and then we're going to talk about what made things open source. So first, let's talk about class conditioning and guidance. So we have looked at so far, all the models we have looked at mostly are unconditional models, which is we give it a data set and it predicts P of X, or models P of X, which basically just says it just generates images from this data set. However, when we do generative models like these, we usually want it to be a lot more specific. Specifically, we want to condition it on more information, right? Specifically, we want to guide it to improve our generation quality. Because one of the things that people found is that by conditioning the model on more information, it actually does better on generation quality, because instead of compromising on a certain loss for all the different outputs, you're telling the model, you just have to worry about generating a picture of a dog, or you just have to worry about generating a picture of a cat, and that generally improves image quality, right? So basically, we're predicting now P of X given Y, where Y is some condition. It can be text, can be a class, can be anything, right? Or it can be a combination of different things. Again, this is not a new idea. This has been done like since the previous generative modeling paradigms, even beyond CV. Like people do this with GANs, with regressive models, with autoencoders, all that stuff. So first, I want to talk about how people gone about doing class conditioning. This started with this OpenAI paper called Diffusion Models Beat GANs on Image Synthesis. It's around the time when diffusion models started becoming better than GANs, which is they basically added both time embedding and class embedding, both projected, into AutoGN, which is basically adapting to instant formalization, but like they did something slightly different. It's not very important, but the idea is that they say, oh, we can generate class inject class information into these models, and it generates better quality images, which is pretty nice. However, here's the problem, right? What people have realized is that this is good, but it's still not the highest quality. So around the same time, the same like Yang Song paper, which is this paper, also proposed another thing, which is something called classifier guidance. And classifier guidance works a little bit differently. First thing, you train an image classifier on image S, for example, on your data sets. That means it takes an image and predicts the class. We know what a classifier is. However, there's one caveat to this. It additionally knows how noisy this image is, and you're giving it noisy images. So keep that in mind. You're giving it noisy images. And specifically, when you're doing image generation for a certain time step, you first predict, you use this to predict the next time step, so you get a noisy image. That noisy, you pass this noisy outputs into your image classifier, and say, in this case, one generate an image of a panda. You ask, is this image panda? And then you back propagate that loss all the way back to the original noise, and you basically says, I want to push this noise in a direction such that it maximizes the probability that this image classifier thinks that the image is a panda. So specifically, if you were to like look at the action map microvalues, it's trying to maximize. It's trying to maximize the entry in the probability outputs of this image classifier that corresponds to panda. And then we have a delta of how we're going to push this noise in order, or like how we're going to push this inputs in order to get to an image that looks more similar to panda. Then we take that delta and we apply that additionally to our inputs, to our noise, and then we pass through the image again. We do this iteratively. So what we're really doing is at each step, we're nudging the image closer and closer and closer and closer to panda as we're doing the noising. And this process is called guidance. That's what we decided to call it. And specifically classifier guidance, because we're using classifier to guide the model. And this works pretty well. Like this is what the original 2020 paper proposed, but there's two problems. First thing is, the classifier must be noisy, which means we have to train the separate classifier that has to be able to take in noisy images, right? Because that's what we're inputting into it. And the second problem is what we're basically doing is we're basically doing an adversarial attack on the generator every single iteration, which means this is not very stable because we're literally just doing backpropagation. That is by definition how we do a lot of like FGS and all that stuff. So a lot of times this is not the most stable thing. So
like it could just push in like towards one panda image or something like that?
It can either push towards one panda image or some artifact in the image that happens to fool the classifier into thinking that's panda, right?
Yes, yeah, so because it's all dependent on the classifier. The classifier,
it's all dependent on
I really think this is a panda.
And you're like, no, that's just an image with a red pixel in this very position. And for some reason, that happens to make you think that I think it's a panda.
Yeah.
If you guys have seen FGS, it's basically saying we can take an image, do a little backprop to that image itself. So shift that image a little bit. And before the classifier thinks, oh, this is a bird, and the image is of a bird. Now it thinks it's an image of a cat, for example. You can do stuff like that. And that's what we call adversarial attacks. It's a whole different field of AI that I think is also very interesting. I can get that's another thing at some point. Another thing is, by the way, this just directly conditioning it on a model is pretty good, but people have found that image quality is actually still not as good as we can have. And this is when, this is the same guy who proposed DDPM, we're so back, proposed something called classifier free guidance. No backpropagation. We're just using the property of the model itself. First, we train a model as usual. We train it with an image and we give it the class condition. So we're training it in the exact same way that we would train, say, a normal diffusion model with condition that we would do. However, during inference, we do something a little bit different. Instead of just making our noise the actual predicted amount, we make our noise this expression instead. And I want to walk you through what this is. First, it is basically the noise that with condition subtracted by the noise without condition. Because specifically, you're training with a certain probability, say 10% of the time, you're training the model with a null class, with a null condition. Okay, you're telling it, I'm not giving you any conditions, just generate whatever. I'm deliberately not telling you what condition this is. So what this is doing is this is saying, at every single denoising step, push the model towards the direction that fits this class and away from the direction which has no classes. I want to reiterate this. We're pushing this in the model towards the direction that fits this class and away from the direction that basically says this corresponds to no class at all. And by doing so, we're able to more strongly generate an image that fits that class. And you can see as we increase this classifier guidance term, we get images that look less diverse, but are more strongly correlated towards, say, husky class, I believe. Right? I don't know what dog. I actually, that's a husky. But the idea is that larger guidance, it makes the condition even stronger. So we actually have a way that we never actually put into the training, right? This is purely on inference time, right? Yes, we're doubling the number of times we're doing inference, like we're never putting this into training.
So you don't have to train a classifier.
We don't have to train a classifier.
And
we have a way to control how strongly we want the model to adhere to the class.
And there's no like weird thing of depending on the classifier.
No, because again, like it's just for training on the model, right? Like there's no adversarial attack.
You have to train it though.
Yes, you have to.
You have to do some training with no label.
Exactly. Like usually what you do is like 10% of the time you train it without labels.
Oh wow.
Yeah. Like it's some very relatively small number of amounts. Like 10% is usually, I believe, at least what it's fake. Yes.
Right, so does it mean you have to train it again for each of these conditions? Like train it to generate noise with huskies? Or how do you get like E, theta, ZT with the condition?
So in this case, basically we train a model without a condition. Like usually we have some sort of like null token that basically says this is no condition. And so because we have trained it like that, the model knows what happens when you don't give it a condition. So it's like this is all happening in the training process. And it's like only a small percentage of the time you do that. So it doesn't really affect the training that much.
Okay, so the rest of the time you train with condition?
Yes, the rest of the time you do train with
In
condition.
the previous one, you always train with a condition.
In this one, for a small portion of the time, you train without a condition. So it doesn't really affect training that much, but you can do this really powerful thing for classifier-free guidance. No graph propagation, because graph propagation is also a lot more expensive because you have to do
In
sparse
time,
and stuff like that, right? And so it takes a lot longer. And so you actually have this like term you can choose to say, to have this trade-off between diversity of images and how strong you want to correlate to your class.
That's so smart.
It's incredible.
That's so smart.
Like early diffusion research, some really good stuff there. No background. Okay, now let's talk about text conditioning, text image models, is what we're here for. So the problem is, how do we turn text prompts into vectors, right? There are many different ways of doing this, but this is what OpenAI came up with. They were doing this more for representation learning, but specifically, their proposal is that traditional text embeddings don't work because they don't contain visual information, right? So they came up with quip, or which stands for contrastive language image pre-training. I actually added, compared to last time I did this, I added this slide because last time I forgot what quip stands for. But the idea is this. You need a data set of a bunch of image and caption pairs. So you can scrape this from the internet, you can create ones yourself, right? You have image and you have text. And you basically choose a batch of each, right? So you choose a batch of image text pairs. Then you separately encode them, usually with a transformer. You separately encode them into two vectors, each into vectors that are all the same dimension. And then you do the following with the loss. First, for embeddings of text and image in the same pair, we want to minimize the difference, the cosine similarity specifically. So this is low cosine similarity, this is high cosine similarity, right? Using a dot product. So we want to increase the cosine similarity for all images that are from the same pair, and we want to minimize the cosine similarity, aka make them the embeddings as different as possible for text and images in different pairs. We call it contrastive learning. And by doing this, we're able to have, basically, if you have an image and text pair, their embeddings, if they're from the same pair, must be very similar. And because this embedding should contain both image information and text information, when we only type in a text, that resulting embedding must necessarily contain some visual information because it must match some hypothetical image that would have been a pair with it. So that's what clip is. And last time someone asked, wait, can you just use this to generate an image? Like you start from a gray image here, you start with a text, you just keep back propagating to make this image like look like what this text would have been, basically. And like you can do that. People have tried it. It doesn't work very well. But again, the idea is that we have this representation where every like images and text have this joint representation space, which is very nice. You can see how that becomes useful for text to image generation.
You have the banana images.
And this is where we get to what DALL-E and Google were doing around this time. Specifically, first, DALL-E came up with DALL-E 2. You'll be like, well, what about that DALL-E 1? I'll mention it here. But basically, DALL-E 2 is that exact idea. They take an image generator, and they basically just says, okay, we have this diffusion model, we condition on text, let's train a model based on that, right? So this is kind of what propelled everything into the spotlight. And it coined the term AI art. And basically, they projected and added clip embeddings into existing time embeddings at a resolution of 1024 by 1024. I call this the GPU go Blurb method because it is very slow and very expensive, and this model is actually pretty big. It was never obviously open weights, but like it's known to be pretty slow and pretty expensive. And in case you're wondering, DALL-E originally was actually a BQB that they were conditioning with text. And then they also have this glide situation where they use the clip guidance, like imagine classifier free guidance, where you're actually doing text instead. That so these were kind of two former iterations of what then became DALL-E 2. Then we have Google's ImageGen, which has a lower FID than DALL-E 2. And by the way, FID is the Frechet inception distance. Basically, lower means it fits the data distribution better. So usually that means it's better quality. And that's a metric that we used to use quite a lot for image generation models. And the main contribution of it is twofold. The first thing is it says, instead of generating a high resolution image directly, which is very inefficient, we do multi-stage training. Particularly, we start by training a 64 by 64 model, right? So very small, tiny image generation model that's still conditioned on text, right? And then we train two super resolution models. First, that takes it from 64 to 256. Another one that takes it from 256 to 1024. You may be like, wait, super resolution models at this point already existed. How is this any better? The thing is, this super resolution model is conditioned on the text. So it knows, so it's like half a generator and half a super resolution model. So it knows not just how do I upscale this image, it knows how do I upscale this image, but I also know what this image is supposed to be, given the text prompt. So that's very useful. And this is very nice because if you want to do, say, guidance stuff, you just do it on a 64 by 64 model instead of having to do this really big model. And you get this flexibility depending on the resolution of the image that you actually want.
It kind of feels like the mapping one with like we're giving the information at every step.
Kind of, but then the mapping one just does all the way to like high resolution anyway. But this one actually, like these are intermediate stages. You train this step, and this step. The
first one is that diffusion.
Yeah, this.
So you do a diffusion, generate a small one, and then you upscale, and that's just one shot.
Upscale. And
the upscales are one shots.
I believe so. Yeah.
Okay.
So. Yeah, one of the problems with 1024 by 1024 is it's kind of limited by the base 64 by 64, what the base 64 by 64 can generate, and it's kind of still just super resolution. And you've been wondering, okay, wait. The second thing that it says is that we don't have to use all the stuff that we talked about before with contrast. We don't have to do that. We can just use T5, and that's just a large language model. It's a good old large language model, and that's actually the second contribution of ImageGen, which is you don't have to use some sort of like weirdly contrastive learning thing. You can just use any large language model and just go with that. Specifically, what you do is like the way at this point how text embedding works is because remember, if you have a series of text and you were to encode the words, what usually happens is the resulting is a list of tokens, right? That's how large language models work. The nice thing is you can just take those tokens, after a text encoder and just do cross attention between that and your image, and your intermediate features image. Because your image already has stuff with it. So you just add a cross-attention layer right after it. This is all with a convolution layer before. And that's how you do image generation. That's what an intermediate layer of one of these units look like. So you use cross-attention for text conditioning, which kind of makes sense because you're trying to say, okay, we have this output table, we're trying to inject information from this text encoder and use cross-attention to do that. So yeah, that's how we inject text at the time. Then we get to the thing that became open source, which is something called a latent diffusion model. Specifically, what this says is it basically says, okay, training a diffusion model to generate a 512, say a 512 by 512 image or 1024 by 1024 image directly, that's too costly. It's very high in resolution. We have really big loss, takes a lot of resources. However, what we have already is an autoencoder. What if, kind of like what we did with the VAE before, I should have a better way to do this, but kind of with the VAE before, but instead of using some sort of pixel CNN, why not just use diffusion to generate what's inside? We know diffusion works really well, it scales up very nicely. Why not just use diffusion to generate what's inside? And that's exactly what latent diffusion model did. Latent because we're generating instead in the latent space versus the image space. The idea is to compress a 512 by 512 image into a 64 by 64 much smaller latent image. So all we have to do is train a text-to-image model in the 64 by 64 latent. And the advantage of this versus, say, Google's Imagen, because they're also kind of doing a 64 by 64 diffusion model, is that this latent model, because it's a latent space, doesn't have to look like a final image. That latent can look a little bit wonky. It can try to contain more information than a 64 by 64 RGB image would, even though it's not actually much bigger. So you're having a richer latent representation inside that allows that may be a weird distribution, but the nice thing about diffusion models is they can model any distribution. So it doesn't matter if your distribution is a little weird and a little wonky, the diffusion model can learn that. And that's the idea. And which is why actually most modern diffusion models nowadays are all latent diffusion models. Almost every single model today you will see has a VAE wrapped around it. Which is why there's also a lot of new VAE research that's like, how can we compress this stuff better? Because the better you can compress your VAE do compression, the smaller your internal model has to be, or the higher your resolution outside has to be, right? So yes.
Do you need the compression? You just need decompression, no?
Yes. When you're training, you need the compression because you need to actually know what your target latent is. But when you're doing inference, you don't need the encoder.
You just like diffuse on a latent.
Yeah, diffuse on a latent, and you just use the encoder. During generation, you only use the encoder. But during training, you can see how we need an encoder because we have a real image that we need to figure out what its latent has to be before we can do this diffusion process, right?
Oh, okay.
Yeah.
Okay, yeah.
Exactly. So that brings us to Stable Diffusion. Stable Diffusion is basically around this time is when Stability AI reached out to the original authors of LDM at a university in, I forgot the name of it, but a university in Germany. And basically they said, hey, we're going to give you more compute. Let's make an open source model. And that's basically what kicked off so much research that we're going to talk about after this, because this is open source. People can play around with it. People can do all sorts of stuff with it. And this really made, I would say, like AI, like just image generation accessible, because instead of it being locked behind an API that you pay money for, as long as you have a gaming laptop, you can run this, right? You have a gaming laptop with some VRAM on it, you can run this, right? And this model, so to kind of summarize, you have an encoder that encodes things into latent space. So we start, and when we're generating image, we start with some noise for S64. We do this iteratively generation process with text encoder, and plus we're also using classifier pre-guidance on this. But just now with text encoding. So like 10% of the time we train without a text embedding. After this, we generate a latent image. I'm just using a inverse image as an example. Usually looks a little bit weird in this. And then we just decode it to get our final image. The Stable Diffusion was trained on Lion 5V, which is scraped internet image alt text pairs. You can see why that becomes very problematic really quickly. For example, recently, like a few months ago, people found a concerningly large amount of child pornography in Lion 5V. Because the thing is, Lion 5V is not violating any copyright constraint, because instead of being a data set of images, it's a data set of links to images. So all it's giving you is this huge text file, and it's your job as machine learning scientists for training stuff to download those images. So the responsibility is not on Lion. They're just giving you a bunch of links, and it's fine to share links, right? Fun fact, when this whole thing came out with like Lion probably having a lot of really questionable data, UCLA CS and a lot of CS departments around school actually emailed researchers, including me, being like, if you have Lion 5V on the hard drive, don't just delete it. Contact because they have like DMEs, like people who deal with this sort of stuff in the departments, but contact them. They will tell you the next course of action to deal with this. And please, whatever you're doing, stop training with that data. Stop using that data. So that's a thing that happens. And another thing thing is Stable Diffusion actually is also a lot smaller than Value2 and Imogen. Especially since Imogen, it uses T5, which is the same as 4.8 billion parameters. So Imogen is actually really big in total. Where Stable Diffusion uses quip, which is only of like 130 to 200 million parameters, which is a lot smaller.
Also, the clip isn't like OpenAI, it's or did
no,
OpenAI
OpenAI actually open sourced the clip.
Oh, okay.
Yeah, the clip is open source. However, later with Stable Diffusion 2.1, they decided to train all on open source data. So like I believe they used like a better version of Line5 at that point, and they also use OpenClip, which is a open source version of Clip. Okay. But yeah, so there were some improvements later. You know, Stable Diffusion XStyle came out, which basically is a paper on data engineering. It's like how can we tell the model how high quality a data set is, and how can we do training so that we kind of scale up on the resolution, scale up on the quality. So that produces better quality images. And DALL-E 3 basically is another data engineering paper, but on the idea of how can we generate better captions. Because the problem was we were using alt text for captions, which is basically it's for screen readers and for accessibility reasons on the internet. But the problem is a lot of times for alt text, people will just fill with like ads because of SEO. So a lot of those alt texts are actually pretty low quality. So what OpenAI did is they said, what if we just train a really, really, really good captioner? And they realized that a lot of the problems with diffusion back in the time were like, it doesn't follow your prompt. It's just, a photo of a banana next to an apple. It may only generate a photo of an apple or only a photo of a banana, right? It can't follow prompts that well. All they showed us that, the reason is because our prompts in our data set were crap. If we have better prompts, they can follow prompts really, really well. And that's basically what DALL-E 3 showed. So now we're sort of all caught up in text-to-image modeling at this point. And these are the papers that we have covered so far. Okay, so let's see how much time we have left. We have 30 minutes left. We're not going to go through all this, but here are the rest of the papers I planned for the rest of this presentation. We're not going to go through all of this today, but we'll figure something out. Maybe we'll skip video generation for today, but we'll go through as much as I can. It also depends on if the studio kicks us out or not. So let's get started. Part 1, controllable generations. This is starting to get to my turf, basically. Like, this is what I do in research. So I'm pretty excited about this section. So let's start with what is controllable generation in the first place. This is what we have so far. We have an image generator. Let's ignore the VAEs for now. And we have a text encoder. The question becomes, can we condition these images on stuff just besides text prompts? And the idea is yes, we can, right? We can condition on something else in addition to text, like for example, a depth map of the image, say a sketch of the image, maybe making a certain word more prominent. Maybe you want to inject an identity of a person. You just want to generate, say, pictures of our team, for example, right? Okay, you can do that. So one of the first papers that really made this idea of controllable generation really popular is ControlNet. What ControlNet is it basically says with any condition that is spatially correlated to our image, like say a picture of an outline or a picture of say like a pose of a person. And if you look at the original like paper or like the demo, they have a lot of different conditions. Like for example, they have like blurb, like outlines. They have HD maps. They have depth maps. They have they have a bunch of different conditions. Like you can even do sketches and have it generate like semi good looking images. You can do something like that, right? So like that was the thing that they did. And the way this works is they basically said, okay, because our stable diffusion is a unit, if you remember that, we have a sort of encoder portion and a decoder portion. They said what they realized is that the encoder portion is an actual literal encoder, because to generate an image, you must be able to understand an image very well. So what they did is they took this encoder, made a copy of it, froze all the weights of the stable diffusion model, and they basically trained a separate encoder that takes in your condition. It encodes it, and it injects with zero convolution. Basically, it's like a sort of weighted gating of like basically saying a convolution that's initialized with all zeros. So at the beginning of training, because it's all zeros, it doesn't affect the actual image output because you're just inserting zeros. But as you train it, the zero convolution becomes scaled up to something a little bit bigger. And that's why you're doing this gradual training where you're never actually destroying the image quality, right? And you're injecting this into the decoder part of this diffusion model. And you're able to do really cool stuff like this. And that's ControlNet. Yes.
Okay. I guess train it to like listen to the input, like those.
Right. So what you would do is you would just basically keep fine tuning it on the diffusion objective, but instead, so what you would do is say you take an image, like you have an image triplet, if you will. You have an image, it's sort of whatever condition you're training it on, and then a caption that goes with it. You will just still do the normal thing, which is you pass that image through an autoencoder, you noise that results, you pass it through the model and try to predict the noise that you added. But additionally, this time you also pass this in. You pass this in also through the same model, pass it through, but it adds information to it. So you're basically just doing more fine tuning, if you will, but then now you're adding additional information.
How do you guarantee that the gates will turn off?
So basically, what the internet authors did is they said, hey, we trained it and it turned on.
Oh.
And also, they also said like they actually addressed in their paper, or at least on their GitHub repo, that some people may be worried that zero convolution mathematically gives you zero gradients, but they did a derivation that says with convolutions at least, no, it will not give you zero gradients. So it's kind of guaranteed that the convolutions will eventually be like the gradients are not zero. And another really interesting thing in their paper is that they were showing how the training process actually looks like. So here is what it looks like. So they were using a test input where they're just saying, you know, an apple, right? And they're only training on this image. They realized all the training steps, it never really quite gets it. So the convolution is still kind of at zero, or like not big enough to affect final image. But at a certain step, it snaps. It snaps to suddenly be able to understand it. And that's kind of what control net training kind of looks like. Is at a certain step, like I've trained control nets on my own before as well. It just kind of snaps onto the output, and you go, okay, it has understood it. And you can kind of understood it as, at that point, that's when zero convolution figure out, okay, the zero convolution has become not zero enough that it actually starts affecting the output of the image, basically.
Wait, so there's no objective. You don't have that actual output image condition on it at all.
You do.
You do, or you do?
Because this is usually accompanied with an actual image that you use to get this in the first place.
Oh, okay.
Yeah, so one of the things with control net is usually you need paired image pairs. So you have a bunch of images, you say use like a depth estimator to estimate a pair of all the depth maps of it, or you use like a line, like a line generating kernel to generate like candy maps, for example. So that's how control net works.
Is it still classifier free? Or
okay, all of these are using classifier free guidance in the generation process. And in this case, classifier free guidance, you're still giving it the structure. You're still giving it a condition, but you're just not giving it a text. So it's the same thing.
So at training, or inference, what would you do? Let's say I don't have the image of the. I only have the stencil drawing. Let's say
you can't do that. You have to have a paired image.
So what about inference time?
Inference time you only need this because you start from noise, right?
Oh, but at training time you have the image pair and you like slightly noise
you
that.
You always need
and then it's like. Yeah,
and you just use the diffusion ones, but this time you additionally add this thing. Yes.
So when you're calculating the loss, is your parent image also used as part of the?
Yes, you are. Yes, it is. In fact, you're just doing normal diffusion training, like you're just doing additional training, but you're adding in this additionally as well. So you still need the original parent.
Oh yeah, it's like you have text you're conditioning on, I'm conditioning text and this thing, and I want it to output.
Yeah, exactly. So you're just getting extra information. And Collision does a very similar thing, but this time it does bounding box conditioning. And specifically, it kind of was one of the first papers to use a discrete condition, because if you think about this is kind of continuous. This is kind of continuous. It has to have a one-to-one mapping to the image. But Collision, what Collision said is, hey, we can have this one-to-one image situation, but we can also just encode like bounding boxes, right? And this is like literally it's just like a sequence of numbers that you're encoding. And basically what it does is instead it uses cross-attention. It trains a new module that uses data self-attention, which is kind of the same as zero convolution, but instead you're just like multiplying the outputs of this by like a vector of a bunch of zeros that's trainable, and you're just kind of slowly those vector of zeros become non-zero, and that's how you start affecting the image. And by doing this, you're able to achieve kind of both control net-ish looking things, but also get like discrete inputs as well. So it's very similar to control net, but instead they're using like a separate. They're not like copying the thing, but they're using like a separate like a strained like data detention situation, where they're doing cross attention with your condition image, but your condition image is encoded by some set, say CNN.
In both these setups, you do have already a pre-trained model just on text.
Yes, all of these start from a pre-trained diffusion model, and the reason why I say stable diffusion is so important is because it gave some people an open source model to be able to do stuff like this.
Costs so much to do that. It's
yeah.
Like, and because,
the bulk of the training is the pre-training, aka like the training the actual stable diffusion model itself. These comparatively are much cheaper to train because you're basing it on this base model that was already trained. Does that make sense?
Which was conditioned only on text, and now
you're
adding,
conditioned on text. And now you're adding this additional model.
Yeah. To like let it learn.
And in most of these cases, you're not fine-tuning the model itself. You're freezing its weights. You're only fine-tuning the module.
Like little adapters.
Yeah, an adapter. In fact, speaking of adapter, this is part of the big paradigm, which is by doing control using adapters. So this is one of the first works to do with T2I adapter. All the 3 control works I just showed you are all concurrent works. Like they're all like February or January of 2023, right? And specifically, this says, let's just need a little more detail. We have a bunch of adapters that does some classic fully connected layer stuff, and then you just do cross attention inside the units. And specifically, what they said is you can actually kind of have a bunch of these adapters for different types of conditions. Like, for example, you can have an adapter for pose information. You can have an adapter for depth map, and you combine those together actually to do cross attention at the end. So what T2I adapter showed is that you can have this really sort of flexible way to add condition to a model by having this additional module. Because the thing about control net is pretty big because you're basically taking half of the model and just copying it over. But these adapters, what they have showed is you don't have to do that. You can just train much smaller adapters from scratch, and you have a much more lightweight way of actually doing conditioning. Control net does have the advantage of it usually being much better at like pixel to pixel coheres, like it's more precise when it does conditioning. But with conditions like pose images or whatever, like generally with Legion and with T2I adapter, it's a little more loose, right? It doesn't have as strong of a pixel correspondence, but it's like good enough for most cases. So that's the sort of controllable generation works that we see. And also the same group later came out with IP adapter, which is basically that, but instead this time you're training it on like human face and stuff like that. This is how like, if you've seen like images of like people like, oh, I made myself into AI. And like there was this like one startup before I was like, I can make LinkedIn headshots for you. If you upload images of yourself, and I can make professional headshots of you. It costs only $15 a month. It literally just uses this. Like a lot of these models that you see, people are like, ooh, you can make images of yourself and like a LinkedIn post that looks like this, right? That's amazing. It's just IP adapter. Like these are all just taking open source models, wrapping it around for some application and selling it to people. It was the kind of the Wild West in the sense of that people were just doing anything with this before like the public really caught on to be like, okay, this is how these actually work, and I can have access to this if I have a bit of coding knowledge, right? So that's kind of side note to that. But then we get to training free image editing. All of these still require training something, and that's expensive. So can we like just use the diffusion model itself to do stuff? Like, because the diffusion model have really powerful and rich intermediate representations, right? What if we just manipulate those representations, like what we did with style transfer before, to try to do image editing? And the answer is we can. So specifically, this was a paper from Google, prompt to prompt. They actually used ImageGen for this, not Stable Diffusion. But the idea is the same. Their observation is that because you have this cross attention between your text prompt and your actual image that you're being generated, you can actually look at the attention maps of each of the text tokens to your image, and you actually realize they actually kind of almost create a mask, because that's what it's attending to, right? That's how attention works. Our team loves that right now. That's what that's attending to. And what you can do is you can say, oh, I want to make this bear more bear. You can just take these attention maps and just increase it. You just make the attention like activations higher, right? So you can do things like make a thing less crowded, make a bicycle by replacing with the attention map of a car. You can take landscape with a healthy river and add a rainbow in the background, right? So you can do all this sort of stuff by just messing around with the intermediate attention patterns. Oh, my internet's unstable. It's fine.
I think you can even do this with LLMs. You literally just get like a prompt of like happy people, and you get them coding, and then you just like
you just add it
or get rid of it.
And yeah, there's another side to remind you, like the way these models work is you have a convolution layer, you have some attention, and you have cross attention, which is where the text actually comes in. And we're messing around with the cross attention layer. And kind of also a side on this, to be able to edit real images, you have to do something called inversion, which is basically the idea of, okay, we have this final image that I have. What would be the noise that would have, and text combination that would have generated this image, basically? Because to be able to edit images, you have to be able to start this image from noise and then regenerate that image, but you do editing stuff to it. So this is something that we call, so there's kind of 2 approaches to this. DDI and inversion, which basically says, instead of starting from noise and iteratively adding noise, starting from noise and iteratively removing noise to get to an image. We start with an image, pass it into generator, it tells you the noise delta, and you basically use that to say, even though that's noise delta of this image to an even more denoised image, we assume this delta, it will be the same as a delta to get from a slightly noised image to this image. So you do the DDI in reverse, and you get to an encoded image, and generally that does like okay. It's not a bug, that is a bug. Anyway, so And then there's null text inversion, which basically says we're doing this kind of VAE inversion process, but instead we're doing so while optimizing for the negative classifier-free guidance null text token. So you're using the classifier-free guidance token to basically say, I'm optimizing that. So like I'm optimizing that so the final image looks like the original image, basically. So that's two ways of doing it. And prompt to prompt use null text inversion. But so there's, and then people later have to figure out better ways to do inversion to do image editing. I won't get into that today. So, okay. And around something like this, when someone proposed something called plug and play, which is the idea of basically like, hey, we can just like replace the attention maps. Specifically, we replace Q and K, which is the attention map. We just replace the attention map and then transfer structure over. Like we just do that, and like that works actually very well. Like especially with real images, like like these intermediate attention layers are so powerful that you can just do stuff like this, and it generally will work. And the important reason why this works in the first place is because the diffusion models are self-correcting. When you first do this attention map injection thing, it may generate an image that's a little bit wonky looking. However, what the diffusion model does is because it has self-attention, the self-attention layer looks around at the image and goes, okay, I want these things to attend to each other. This looks a little bit wonky. I'm going to get rid of that. Like, again, I'm anthropomorphizing the model itself. But like, you can get how like self-attention is making sure the image has global coherence. Actually, one of the things that Pratik did, was the former project director did, was he was training his own diffusion model, and he forgot to add a self-attention layer. And he was training it on like an image data set of a bunch of like cars. And he realized when you don't have a self-attention layer, sometimes the car lights may be all over the place in the image because it doesn't have that global coherence, right? However, if you add self-attention, it adds that global coherence. It was a pretty cool little experiment that he randomly stumbled upon because he forgot to add self-attention into his model. But yeah, so this is something that you can do. And here's another one called pix to pix 0. This one does control on the text encoder itself. It basically what it says is this. Let's say we want to find a direction to make all cats into dogs. Then what they did is they went to GPT-3 and it says, give me like 100 captions that includes the word cat. And then it says, give me 100 captions of captions that includes the word dog. It fed each of those through clip and then just average that vector, average this vector, and it says this delta is our edit direction. And you just apply that to your text encoder, or like you apply that to your text embedding, you get a pretty good you can actually achieve editing like this. So this is a pretty brute force paper. One of the reasons why this actually works is because I believe the way clip works is because the output embedding is actually just a CLS token. It's actually able to just have one single vector that it can edit.
How is this different from the ImageN one? You're just like changing the prompt and then getting it.
Yes, but this one you're changing the prompt like embedding itself, the token itself. Whereas the one before, you're changing the attention layers, which is different.
Wait, can you go back to the? So
this one you're manipulating the attention feature maps, and this one you're editing the actual tokens before they even go into cross attention.
Oh, okay.
Yeah.
So they change the prompt, then look at the attention maps and do the difference, and then here we're just doing before it even goes in. Okay.
Yeah, exactly. And there's some further stuff that basically says, hey, we can do like a bunch of like weird masking stuff that corresponds with text to actually do like kind of dense text prediction. We can specify, I want a person riding bicycle here, I want a moon here. I'm not gonna get into this too much, but like there's been a lot of works that looks like this that basically just says, hey, you can mess around with the attention layer. It gives you controllable generation. And then we can get back to guidance. So this paper, Guidance Zoe, that basically kind of formulates saying like, oh, we can have a slightly more complex guidance way of like, oh, we pass this noisy image through some sort of model, but instead through some sort of model loss. If you were to say feed it into an image classifier or like some sort of image understanding model, you probably do X0 prediction instead. And you pass it back into the noise and you just use that to additionally, you add that to the classifier-free guidance term. And by doing this, you can basically kind of, before with classifier-free guidance, is I'm pushing the model away from generating an image that doesn't have any prompts, basically. In this case, you're pushing the model towards some loss. So in this case, you can say, I want it to look like this person with a facial recognition model, or I want it to look like, this style with some sort of style like embedding model. Or like I wanted to have this person here and this dog here with some sort of like bounding box general.
This is the exact same thing as classifier.
It's the exact same thing as classifier guidance, but they extend to say this works with anything.
Okay.
Yeah.
That's class.
Yeah, and they added some more complex things to be like with more complex types of conditions, this becomes more unstable. Here are ways that we basically almost do like a mini gradient descent to make it even more stable. And then you have the fusion self-guidance. That basically says if we want to do things like then test, like if you want to drag things around, like for example, you have an original image, I want to swap the positions and all that stuff. Instead of having to find some additional like outside loss that like we really have to pass the image through the VAE and into some sort of bounding box model, and passing through that VAE is very costly. Instead, let's just look at the intermediate attention features and just say, what are the centroids of this? Drag the centroids to swap them, or like take this attention feature map, I want to make that bigger, and stuff like that. So you can just do losses directly defined on the intermediate attention itself, and you can do guidance.
I don't like that.
If you don't like that, yeah.
It works. It works.
It works very well.
What?
In fact, you'll see a more ridiculous example in just a little bit. Fine-tuning. So fine-tuning, Laura is the thing that basically says, hey, instead of we can approximate a pre-trained weight of say like d times d by doing two separate matrices, d times r and r times d, which basically approximates it to be much lower. You can see how this is much smaller than this original weight. And basically this was first proposed for LLMs, which basically said when we're fine-tuning, instead of fine-tuning the weights itself, which is very costly, we just fine-tune an additional, this sort of low-rank approximated weight that is much smaller and makes it so that, first of all, it's much cheaper to fine-tune. But secondly, if I want to give you a fine-tuned version of my model, instead of giving you a different copy of the weights where I fine-tune, I just give you this additional tiny little Laura weight thing, and you just add on to your existing weights.
It's recording the difference.
It's recording the difference.
That's the most important thing.
And the most important is recording the difference. It's not recording the weights itself. So you basically you're assuming the person still has a copy of the original model weights. But if you have a bunch of different Lauras, you can see how that becomes a lot more efficient. Of like, especially people sharing like different sort of fine-tunes. And you do that with image models as well, basically, that's what I'm saying. And there's this other paper called Dream Booth, which is kind of like IP adapter, but then you are fine-tuning on a single image. Specifically, what this does is it says every time when we're saying, like we have a picture of a dog, for example, we want to generate a picture of this particular dog. And I want this particular dog to be associated with a certain token, say this token, right? Like let's say assume there's a certain token. What we can do is we say, I have a bunch of pictures of this dog. I just fine-tune the model on saying a picture of this dog, and I just fine-tune it on these images. The problem with that is if you just fine-tune a model of that, when you try to generate pictures of other dogs, it just keeps generating pictures of this dog instead. So what you can do is you add an additional loss term that says, when I generate images that are not of this dog, say images of normal dogs, I don't want them to look similar to these. So by doing this sort of regularization, you're able to generate, basically make sure the model is fine-tuned onto the identity of the object you're fine-tuning with, but without it just collapsing on this set of images. If that makes any sense. So you can do stuff like this, like where you fine-tune on this dog and you say, oh, the V dog in, Parabolas, or the V dog in a doghouse, the V dog in the bucket, and you've started to associate this token with this dog itself. And usually what you do is when you're fine-tuning the model, you will also fine-tune the text encoder, so it also updates the embeddings for this V specifically. Any questions on this?
To not overfit, just make sure the rest of the stuff you still get good loss on. Is that like
yeah?
Contrastive thing.
It's kind of a contrastive thing. Right? Like I think they do take inspiration from contrastive losses. All right, it's 52. I hope students doesn't kick me out. I want to get through section 2 of this. Okay, so this is where we kind of combine like the idea of like what we talked about guidance before, with like the whole like the sort of self-guidance thing. And basically what this does is it says, this paper says, oh, we can take an image and we realize that all intermediate features, the principal components of them are very similar. So we can just extract their first few principal components and say, I want my output image to align to those principal components instead. And by doing so, you're actually extracting the sort of structure of these images. And because you're extracting the structure of these images, you can actually basically do what ControlNet does, but completely training free with a bit of guidance. And so this was a paper that came out in December 2023. You can read on to it a little bit more. The reason why I want to mention this is because, hey, my name's on it. And a later paper that came out that basically says, hey, let's bring back the idea of like style transfer, and says, if we use like ADA-IM, but like with a bit of attention renormalization, we can actually combine the idea of plug, and play. We're just swapping out intermediate feature layers. By adding this additional like appearance image, you actually regularize the image so that even with images with like weird conditions, like like depth maps or like like 3D maps and stuff like that, you can still generate coherent looking final images. And by doing so, you actually add an additional bonus, which is you're able to do both appearance and structure control, right? So it's kind of like combining the features of IP adapter and control nets. And the reason why I say this again is my name is also known to so yeah. Anyway, so let's get to part 2. I do want to get through this section. I hope Studio doesn't get too mad, which is attack of the LLMs. So it's CCI. I can choose Japanese one as well. Okay, so the reason why I want to talk about this is because a lot of recent diffusion, like especially generative vision research, has had a lot of elements of large language models brought in, and not just on text conditioning. And the reason is because of this. So back in 2020, so this was after like the ImageNet craze, where people were trying to do image classification with really, really big CNNs, right? Basically, some people proposed that, hey, we can use transformers to encode images as well. Specifically, what we can do is we take an image, we divide it into smaller patches, specifically 16 by 16 patches, or like patches which are 16 patches in each dimension. And then that resulting token can just be a sequence in which we can encode, and then our final like CLS token can be used for classification. And what they showed is that even though this doesn't perform as well compared to CNNs with much smaller data set, like 1 million data sets, when you scale up to 300, 500 million image data sets, it starts performing much better. So the sort of scalability that Transformer has starts to become very advantageous here. So people looked at this and went, what if we use this for the backbone for diffusion instead? Because the nice thing about transformers is that input and output dimensions are exactly the same, which is very nice. And this is where diffusion transformers come in. The problem is scalability, right? Like we have all these new models, but the problem is all of them have improved image quality by doing data engineering and by doing like better prompts, basically. There was never an explicit study of scalability, and no one ever studied how scalable like units are. So how do we actually scale things up if we want to scale things up further? And this is where diffusion transformers comes in. And it comes from this the author's the first, by the way, the first author, Peoples. He's also one of the first authors of Sora, the OpenAI video paper. Yes, he's the OG. So he's the one who says, hey, we can use diffusion with transformers as the backbone, and it scales a lot better than units, basically. It scales way better in units, and he proposed this idea of like basically just modifying a VIT to make it work. And specifically, what you do is you start with an image, right? So this is all wrapped around a diffusion VAE. You patchify it, you embed it, and basically you divide it into patches of shape P by P by C, which is your channel dimension. And then you basically pass it through a bunch of different DIT blocks. And the way you do conditioning is by using, we're back to adaptive instant normalization again, which is like, use MLP, use the conditioning to generate ways to generate the scale and biases to scale each of the layers. And at the very end, one special thing they do is instead of predicting just the noise, they predict both the noise and standard deviation. Because technically, diffusion models, how they're formulated, it predicts both the noise and standard deviation, but just a lot of early ones just assume standard deviation equals 1, so they don't predict it. But people later realize that, hey, if you don't assume that, it actually makes better image quality. The output is twice as big, but you can do like resampling and stuff that makes it work. But that's the idea. And the thing is basically there's very obvious trends of scaling. That's what they've noticed, is that when you keep making it bigger, it does perform better. It never really hits a bottleneck. And the most insane thing is, if you take a model and you just keep training it, it just keeps getting better. They explicitly stated in the paper that they had to stop at 7,000 steps, not because it plateaued, but because they ran out of compute. And if you look at the FID, it just kept decreasing and never stopped, which means diffusion transformers are much more scalable if you want to scale your model to be much bigger. So based on that, we have a lot of modern diffusion models. For example, Stable Diffusion 3, which basically takes this idea of DITs and extends it to text-to-image generation. Specifically, they do this like multimodal generation thing where they're doing attention across the text and image, so it gets rid of self-attention. It gets rid of cross-attention for text injection, which works a little bit better because it usually improves text alignment by units. So like one of the trends is they realize text embeddings are actually way more important than you think, instead of just being like a cross-attention thing as like an afterthought. So like basically a good diffusion model should understand both text and image, which seems to make sense. And Flux 1 is kind of like sort of the state of the art right now in terms of open source models. And specifically, it scales things. Specifically, it does something really similar to Stable Diffusion 3, but it uses something that I do want to highlight, which is something called rope embeddings, because it's an example of one of the things we stole from LLMs. I'm not going to go through this right now. I'll go through this next time. But the idea of rope embeddings is instead of each of the tokens, the model has to understand this is the first token, this is the second token, this is the third token. Instead of encoding that in absolute terms, rope embedding says I want to have a way to encode it so that all we're worried about is relative position. So like a token at position 1 and a token at position, say, 10 should not have a difference. The only difference is the difference between the token at 1 and 5 should be the same as a token from at 11 and 15, right? Only relative position should matter. There's a bunch of math behind it, specifically with like complex numbers and like rotating vectors, but like that's the idea behind it. So you have a lot of modern, and also you have a lot of modern diffusion models which tries to kind of put together the objectives of LLMs, autoregressive losses and diffusion losses, by messing around with the autoregressive mask. And you can just generate both images and text at the same time, do image editing. We'll go through this a little bit more next time I talk about this. And also, you also have video code that basically says, if you have a good enough autoencoder that can compress an image down to a low enough dimension, you can just basically model everything as an LLM and just predict the next frames by using an LLM backbone to do multimodal predictions. So this is a paper by Google back in January. Yeah. Okay. So we won't have time for video generations then. Yes.
No,
okay. Any questions?
So you mentioned the scaling of the vision transform.
Yes.
Has anyone done a full paper, I guess, diffusion vision transformers, I guess, scaling laws for that?
Yeah. The original DIT paper does scaling for that. They haven't scaled it up enough to like scaling studies of big text image ones, because those are still costly enough that it doesn't make sense to do scaling like studies on them.
Okay.
Right. Okay. So I'm gonna skip the video part, but one of the things is actually like this is there's a lot of stuff there. This is only part 1 of this reading group. One of the things is that when I decided to do this, I kind of sat down, I wrote down a list of all the topics I wanted to talk about, and I realized there's no way I'm fitting this into one reading group, and evidently I didn't. So a sneak peek of part 2, besides all the video generation stuff, we're going to talk about how video generation did before DITs came along, and how video generations are nowadays when we have, and how open Sora and how Sora works behind the scenes. However, there's a lot of other things in diffusion I want to talk about. For example, first of all, I want to talk about warm gas. I think GANs is very interesting. There's a lot of stuff there I think that we can still talk about. I want to better motivate diffusion models, because I think like the way that I'm doing this, I did speed through a little bit. There are some real like mathematical reasons that I think are very, very intuitive that will make the way that we're formulating diffusion models a little bit better to understand compared to what I have done so far. Diffusion sampling, which is how can this process of like skipping time steps, can we make that better? If currently like 50 time steps is generally like an okay amount for DIM, but like can we do like 10 steps or even 2 steps or 1 step, right? So there's a lot of, because these are all ordinary differential equations and mathematicians have been doing math on this for a very long time, we can apply that to diffusion models. And there's a new thing nowadays called rectified flow, which is a whole other thing that allows you to do close to 1-step diffusion. Distillation, which is the idea of can we make diffusion models take fewer steps, way beyond 50 steps, like 2 steps or even 1 step. You can even use adversarial loss to fine tune the model so there's 1-step diffusion. More multimodal diffusion. There's a lot more details on like joining the 2 objectives that I want to talk about. Autoencoders are unique, which is a sort of survey on all the insane autoencoders people have came up with and how they managed to come up with autoencoders that allow you to generate images or like visually that much better. 3D generation. You can use diffusion models as a critic to optimize neural radius fields, which is like a thing. Our team has talked about this before. We may talk about this in the future. They can generate stuff, or you can just use depth maps to construct and do in-painting to create 3D scenes, or you can just do diffusion in 3D directly. It's a lot of cool stuff we can do diffusion with 3D stuff. Diffusion security, because of the fact that it's very contentious, it being like something that really does hurt the artist community. People have been finding actually we can use ways to poison the data of diffusion models, and there's a lot of security safety issues and alignment issues with diffusion that people have been doing research on. Diffusion with reinforcement learning. Specifically, we can do RLHF fine-tuning to make diffusion fit better to our preferences, and we can also use diffusion as a renderer for RL agents to explore environments. 4 element techniques that we have yoinked from Diffusion specifically, there's a lot of autoregressive stuff. There's diffusion mamba, that's a thing. Everything is diffusion because diffusion are basically a way to solve inverse problems. And people have used for stuff like climate data and stuff like that as well. And also scaling up to massive video models, because a lot of these models are so big, like that there's no way for you to fit it in even the best GPU today. For example, like this comes from, a lot of this comes from LLMs. Like for example, like Llama 3, 4, right? Just putting it on the GPU requires 6 A100 cards, which is the best card that best card that we have right now. How can you train a model that doesn't even fit on a single GPU? How do we even do that? Well, this is where model parallelism comes in, and a lot of training techniques that goes into both LLM training and also video transformer training that actually has to do with what I did at Snap this summer. That I will also talk about next time in part 2. But yeah, some acknowledgements. First of all, Zheng for letting me mess around with this. Sicheng for being an incredibly awesome mentor that I've had. Hannah and Austin for letting me train my first diffusion model. Mostly our team for listening to me. And thank you guys for coming. So yeah, thank you for coming. I hope to see you in part 2, which is probably going to be next quarter at some point. So sometime in like January, February, maybe March. And in week 7, our team's gonna have an actual like reading group, and I hope you come to that too. Thank you so much.